In this lecture, I'm going to show you how to express finitely generated modules in terms of generators and relations. To start with, let's take R to be any commutative ring. And let's take M to be any finitely generated R module. What does that mean? That means that there exist elements V1 up to Vm in M such that if you take any element V in M, you can find scalars or rather elements of the ring A1 Am in R such that V is of the form A1 V1 plus Am Vm. V is equal to this. This is just the definition of being finitely generated. Now if you define a homomorphism phi from Rm to M by saying that phi of Ei is equal to Vi. So what is Ei? Ei is just the ith coordinate vector in Rm. So it's the vector with all zeros, except in the ith place you have 1. Then phi of Ei is Vi, and so if you take phi of A1 A2 Am, it's going to be A1 V1 plus Am Vm, just because phi is an R module homomorphism. And so what we conclude is that phi is surjective. Okay, now let n be the kernel of phi. By the first isomorphism theorem, we have M is isomorphic to Rm mod n. So what we are seeing here is that every finitely generated R module is isomorphic to a quotient of a free module of the form R to the M. Now let's try to understand better this submodule n. Now suppose R is Noetherian. Then we've seen that every submodule of a finitely generated R module is going to be finitely generated. And so that means that n is finitely generated. So that means that there exist vectors x1, x2 up to xn in R to the M which generate M. Right, so there are n vectors which generate n for some integer n. Now let's bring in some matrix notation to write things rather nicely. What I'm going to do is I'm going to denote elements of R to the M as column vectors. So if I have x in R to the M, I will write x as x1, x2 dot 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 xm, where these elements are in R. So I'm going to think of elements of R to the M as column vectors. And so now suppose we have that xi is the column vector xi1, xi2, let me write it like this: x1i, x2i dot 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 xmi. Okay, then let's form the matrix x, whose entry in the ith row and jth column is xij. So it is x11, x12, and how many of these vectors x are there? There are n of them, so I'll get x x1n, x21, x22, x2n, xm1, xm2, xmn. So this is an m by n matrix with m rows and n columns. And what we are seeing is that n is of the form x u, where u belongs to Rn, which is nothing but the column space of the matrix X. Okay, so this is an m by n matrix. You can multiply it by vectors of the form u1, u2, un, n column vectors of size n, and you'll get a column vector of size m. And the column space of a matrix is precisely all linear combinations of its columns. And so when we say that x1, x2, xn is generates n, that means that the elements of n are all in the column space of x. In fact, the column space of x is equal to n. So what we have is that when we look at a finitely generated R module when R is Noetherian, then you can write it as m is of the form R to the m mod column space of x for some matrix x. And what is this matrix? It's of the form, it's an m by n matrix with entries in R. Now once we have such a matrix, we can work easily with matrices which lend themselves to easy computations, as we shall see. Well, easy or maybe complicated, but at least you have a grip on computation. Let us look at some very simple examples of generators and relations for finitely generated modules. Let's start with a really simple example. Take R to be the ring Z of all integers, and take M to be Z mod 6Z. So the most straightforward way to do this is to note that M is generated by the residue class of 1. And so we would define phi from Z to the power 1, it has only one generator, to M by taking 1 goes to that generator 1. This one is the residue class mod 6. And so we get M is isomorphic to Z modulo the column space of the matrix which has just one entry, the 1 by 1 entry matrix with single entry 6. But well, there are other ways to do this too. M is also generated by 2 and 3 in Z mod 6Z. And so we would then define phi from Z squared to M by taking A comma B goes to 2A plus 3B in Z mod 6Z. What is the kernel of phi? Okay, so we would like those pairs A comma B such that 2A plus 3B is a multiple of 6. In particular, if A is a multiple of 3, then 2A will be a multiple of 6. And if B is a multiple of 2, then 3B will be a multiple of 6. In fact, it's not very difficult to show that the kernel of phi consists of vectors of the form 3x, 2y, where x, y belongs to Z. And so what we get is M is isomorphic to Z square modulo the column space of the matrix generated by 3, 0, 0, 2. let's take the next example where we take R to be the ring of polynomials in some field F. And let's take M to be as a additive abelian group F squared, and let's define the action of T as the matrix A equals 0, 1, 0, 0. Okay, so if you take any polynomial in T, it will act by substituting for T the matrix A, computing the resulting matrix, and then applying it to a column vector in F squared. So M is generated by 1, 0 and 0, 1. After all, 1, 0 and 0, 1 form an F basis for M, and therefore they should also generate M as an FT module. And so we define phi. So this phi is going to be from ft squared to f squared. Right? So it will take a column vector consisting of two polynomials pt and qt, and it will go to, well, because it's an ft module, I can write this as phi of pt times the vector 1, 0 plus qt times the vector 0, 1. And as per our prescription for writing finitely generated R modules as quotients of R to the n, we must take this 1, 0 to the first generator and 0, 1 to the second generator. So these are vectors in ft squared, and we'll take it to pt so this is pt times 0, 1. So here we'll put pa times 1, 0 plus qa times 0, 1. Okay, now let's say this polynomial p is of the form p0 plus p1t plus p2t squared plus dot dot dot. Now note that a squared is actually the matrix 0, 0, 0, 0. So when we evaluate p of a, there will be only two terms, p0 plus p1 times a. So this will give us p0 times 1, 0 plus p1 times a applied to 1, 0. But a applied to 1, 0 is 0, right? You do this matrix multiplication, you get 0, 0. So there's no term here. And similarly, when you do it from q, suppose q is q0 plus q1t plus dot dot dot, the higher degree terms vanish, and so now we'll get q0 times 0, 1 plus q1 times a times 0, 1. But a times 0, 1 is just 1, 0. So we will get plus q1 times 1, 0, which you can write as p0 plus q1 q0. So this is what phi does to an general element of ft squared, and from this you can easily see what it means for a polynomial to be in the kernel of phi. If pt comma qt is in the kernel of phi, then firstly q0 has to be 0. So that means that the polynomial q has to have constant term 0, which means that it is t times some other polynomial. So let's just start with that, kernel of phi. So firstly what we have is that the Q polynomial is t times some other polynomial, t times, let's say, beta t. And then what we have is that the constant term of P0 is the first term of Q1, which is of Q. The constant term of P is the first term of Q, but the first term of Q is the constant term of is the negative of the constant term of B. So I can write P as minus beta t plus t times any other polynomial alpha t. As long as I have this, these constraints, these things will be 0, where alpha t and beta t are in ft. And this is just equal to t minus 1 0 t times alpha t beta t. And so what we have is that the kernel of phi is the column space of the matrix t minus 1 0 t. And so what we have is that M is isomorphic to ft squared modulo the column space of t minus 1 0 t. Now one thing you notice is that this t minus 1 0 t can be written as t times the identity matrix minus the original matrix A 0 1 0 0. And this is going to be a phenomenon which will hold in general. More generally, let's fix a finite dimensional vector space V over a field F and a linear operator T. So V is a finite dimensional vector space over F and T is a linear map from V to V. And to this data, you can associate an FT module M. Let's call it M subscript T to denote that it's associated to T. You've seen this construction already. As an additive abelian group, MT is just V. And the action of PT on a vector V is obtained by taking this polynomial P and evaluating it at the linear operator T and then applying the resulting linear operator to V. So if Pt is the polynomial P0 plus P1t plus dot 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 plus Pdt raised to d, then P of capital T is the operator P0 times the identity of V plus P1t plus Pd t to the d. This is again a linear operator and you can apply it to the vector V. Now if you pick a basis of V, let's call it E1 up to En, then with respect to that you can write down a matrix for T. Say T has matrix A with respect to this basis. What does that mean? That means that the jth column of A is the action of T on the jth basis vector. The ijth entry multiplied by Ei. So this is just the definition of what it means for T to have matrix A. Now we can think of E1, E2, En as generators of M, of the FT module N. Of course there may be a lot of redundancy, but they actually generate MT as an F vector space. They form a basis of MT as an F vector space. Therefore they certainly generate MT as an FT module. Okay, so accordingly we should define, to express it as free module ft to the n mod something, we must define phi from ft to the n, so n generators, so ft to the n, to mt by taking the ith generator here. So let's say ei tilde in ft to the n is the ith coordinate vector. So it's the constant polynomial 1 in the ith place and zeros everywhere else. So phi of will take ei tilde to the ith generator of m, which is just ei. So the question is, what is the kernel of phi? So the theorem that I'll prove now is that the kernel of phi is the column space of the matrix T times identity minus A. We've already seen this in the case of a simple 2 by 2 example. And now let's give the proof in general. So what's the jth column of Ti minus A? So if you think about it, you have t times I, so its jth column is 0, 0, 0, and then there's a t in the jth place, and then again it's zeros. So there's zeros everywhere except a t in the jth place. And then you have to take minus A. So that's just the jth column of A, A1j, A2j, Anj. So you can write this as t times, this is E tilde j, the jth coordinate vector of ft to the n, minus, and this you can write as a linear combination of the coordinate vectors of ft to the n, aij E tilde I goes from 1 to n. And I want to show that the column space of Ti minus A is equal to the kernel of phi. So first I'll show that the column space of Ti minus A is contained in the kernel of phi. And this is just, for this it's just enough to show that each column of Ti minus A is contained in the kernel of phi. So let's apply phi to this column. We get Tej tilde minus summation Aij Ei tilde. And now let's use ft, the fact that phi is an ft module homomorphism. So you will get the action of t on phi of Ej tilde. So phi was defined by taking Ej tilde to Ej. So this becomes t acting on Ej minus summation over I Aij, and I tilde goes to Ei. But how does T act on Ej? Well, T acts by the matrix A. So this is Aej. You think of Ej as a column vector with a 1 in the jth place, minus summation Aij Ei. But you'll recognize this summation here as nothing but Aej itself. So this is 0. Hence, we have shown that column vector or a column space of Ti minus A is contained in the kernel of phi. Okay. Now for the converse, we have some vector which is in the kernel of phi, and we want to express it as a linear combination of the columns of Ti minus A. So let's say if we have a vector in ft to the n, then firstly note that you can write it as a sum of certain very simple vectors. So let's say note that ft to the n has an f basis as an f vector space. It has it's an infinite dimensional, ft itself is an infinite dimensional vector space over f, and ft to the n is therefore also an infinite dimensional vector space, but it has basis t to the k times ei tilde, where k runs over all non-negative integers and I goes from 1 to n. Right, so this is a basis of ft to the n, and let's just look at a basis element here. So if you look at t to the k ej, I can write it as t to the k minus 1 times tej. But this can be written as t to the k minus 1 times, well, this should be ej tilde, tej tilde minus summation I goes from 1 to n aij ej tilde plus t to the k minus 1 summation I goes from 1 to n aij ej tilde. I haven't really done anything. I've subtracted and added t to the k minus 1 aij ej tilde. But this thing here belongs to the column space of ti minus a. It's just the jth column of ti minus a. So this is m plus t to the k minus 1, or maybe I'll write this like this, summation aij t to the k minus 1 e tilde j. And m is an element of the column space of ti minus a. So what I've shown is that if I start with the vector t to the k times e tilde j, by subtracting some vector m from the column space of ti minus a, I can reduce the degree of this term, this t to the k, to t to the k minus 1. Of course, I'll get now, sorry, this should be I, not j. And now I can keep working with these terms and further keep reducing their degrees. And at the end of the day, what I'll get is that t to the k e tilde j is equal to m plus some vector, some vector of the form summation aij e tilde I, where these are just not aij, some scalars cij, where cij belong to f. Step by step reducing the degree, and m is in the column space of ti minus a. So this can be done for every basis vector, and therefore it can also be done for every vector in ft to the n. So every vector v belongs to ft to the m is of the form v equals m plus some vector w, where w is in f to the n, which is, we think of as an f subspace of ft to the n. N here. Okay, and now suppose v is in the kernel of phi. So suppose v belongs to kernel of phi. So now we have v is equal to m plus w, where m belongs to column space of ti minus a. So then phi of v is phi of m plus w, phi of w, where but m is in the column space of ti minus a, and we know that that's in the kernel of phi. So this is 0. So phi of v is phi of w, where w is now just a vector in ft to the n whose coordinates are all constant. They're just elements of f. But so phi of w, if w is of the form summation ci wi, I goes from 1 to n, then phi of w is just if I write it ci e tilde I, then e tilde I goes to ei, so this is just summation ci ei, which implies that, so if phi is in the kernel of v is in the kernel of phi, then phi v is 0. So then this implies that ci equals 0 for all I. which means that W itself is 0. Therefore, V is equal to M plus 0, and M is in the column space of Ti minus A, which means that V itself lies in the column space of Ti minus A.